Welcome to the Heart Rate Variability Podcast. Each week we talk about heart rate variability and how it can be used to improve your overall health and wellness. Please consider the information in this podcast for your informational use and not medical advice. Please see your medical provider to apply any of the strategies outlined in this episode. Heart Rate Variability Podcast is a production of Optimal LLC and Optimal HRV. Check us out at optimalhrv.com. Please enjoy the show. Welcome, friends, to the Heart Rate Variability Podcast. I am so excited for this topic. I've actually been looking for somebody to talk about this for quite a while now. And just recently, I met David Lowenfels, reached out kind of randomly. We connected in the great way the universe allows us to do nowadays. I was just blown away with not only how David thought about heart rate variability, but the depth of his knowledge. So I think, David, I may have asked you after 15 minutes of our conversation, which ended up lasting like 90 minutes, to join this episode. And I know the Baroreflex is a fascination of mine, obviously kind of a cousin to HRV or a sibling, but very important in how we think about heart rate variability with this. And I've been looking for a guest to talk about it. And I am so excited to nerd out with you on this episode on, I know, a shared interest of both of ours. But before we dive in, just give folks a quick introduction of yourself and your interest in heart rate variability.
Yeah, thanks, Matt. So I recently learned the term polymath, and I'm like, oh, that's totally describes me. So somebody who has a diverse array of special interests and sometimes multiple careers, which I'm working on. So I, as an overview, I say I kind of bridge two areas that excite me are the body and technology, in a nutshell. And so I'll go more into that. But so my college education, I studied electrical engineering and computer science with a minor in music and specialized in digital signal processing at MIT. So all the math and computers. So I also do like hardware and software design. But most of my career I worked doing web apps, actually. And then my second career has been a lifelong passion of mine in the healing arts, particularly body work and breath work, but also energy healing and trauma healing, relational practices. So all kinds of cool California type stuff. So I'm currently, I lived in California most of my adult life. I was born in Anchorage, Alaska. I went to school back east, and then I went to grad school at Stanford where I studied computer music. And that was kind of the cherry on top of my education. And yeah, so I've always been interested in frequencies and how they interact with the body and resonance, and studying music and digital music and signal processing and engineering of music. I discovered about, 10 years ago or so, HRV. And I was like, wow, I can, it's, in a way, it's like the music of the body. So all of the math and the engineering and the concepts, the resonance, things like that, the acoustics. So I really think of my interest in this topic, I would call it, in a fancy nutshell, neurovascular bioacoustics. So that means, the blood, the lymph, cranial fluids, the nerves, and how they conduct back and forth between the body and the brain, but also how the nerves are transferring inside the brain, like as we measure with EEG and such.
Yeah.
And it's all part of this kind of dynamic oscillating symphony. And so this 0.1 hertz resonance, which has many different names, so the Meyer wave. So that's, yeah. So I discovered Yevgeny Vashilov's work, and I started, and also heart math, about 10 years ago. And I started, it was when I was working on some cool Burning Man projects with my buddy Mikey from Consciousness Hacking. And so we were doing stuff with light and sound and vibration, creating these interactive art installations. And so I started looking at the cardiac signal processing, like, oh, what is HRV? And read all the papers and like, oh, that's simple. It's just some, basic filtering and statistics, whatever. I can program that in MATLAB. Uh, and then I found a cool USB sensor that was a PPG clip for the ear that could measure stuff. And so I started playing with that and got into developing biofeedback algorithms, particularly with low latency is my interest. So I think that's enough about me for now.
Yeah.
So that my product was called PranaWave. So you can look that up. It's kind of basically a defunct project, but still alive in some ways.
Awesome. Well, we'll definitely throw some information in show notes as well for people to explore. So I would love to just dive in because
yeah, let's do it.
We got juicy stuff to
Yeah,
talk about here
hit
with
me.
the Baroreflex. So this is, I mean, just kind of where I'm at with this is like, okay, you got heart rate variability, like my layman's definition, your body and mind's ability to handle and recover from stress. So we're thinking parasympathetic, sympathetic, and then we got this whole baroreflex thing going on too, which is connected, as the integrated whole that is our mind body. But I just like for the listener who may not have heard this term, I'm sure a lot of may be familiar with it, but there may be some folks out there that are new to this part of our system. Just help us understand what is the reflex.
Sure. So basically the baroreflex is the autonomic network in the nervous system that regulates the blood pressure. So if you think like barometric pressure, it has to do with the pressure, not the atmosphere, but the pressure inside your blood. So it's a very interesting regulatory feedback system because it controls both sympathetic and parasympathetic. So that makes it a cool target for tinkering with the nervous system, because you can kind of get into the back door and access things that are coming and going to the brain, and also that are activating and relaxing all at the same time. So it's a very central target. I mean, yeah. So
when you say, I just want to check a word here because I want to make sure. But you may have used it intentionally, maybe not. But when you say controls the parasympathetic and sympathetic, I'd love for you to expand on. You may mean that in a hey, it's in charge sort of way, or it's influencing. So
yeah,
that connection, because we talk a lot about parasympathetic, sympathetic, ventral vagal, but less so about the para.
Sure. So I mean control from an engineering perspective. So like if you think of a robot, that's controlling things. So it's got like, these levers that can manipulate, three things basically. The vascular tone, which is like how your peripheral blood vessels are contracted or relaxed. So that controls the pressure. It's the main thing. And then the stroke volume, which is kind of like how hard your heart is beating. Those are both sympathetic aspects. So there's two sympathetic controls on that side of the baroreflex. On the parasympathetic side, we have the vagal brake, which is it's the efferent action of the vagus nerve. Most of the vagus nerve is afferent. It's listening to the viscera and even the certain taste functions in the back of the throat. So 80% is listening. It's afferent. But
and sending that message up to the brain, if I'm reading you correctly.
Yeah. But there's some parts that go down, parts that control the voice box, and also like the vagal brake on the pacemaker, which the technical term is the sinoatrial node.
Yeah.
So that's the part that's kind of like the metronome that's ticking inside your heart. It's some cluster of cells in there, and it's normally going pretty fast, like 110 beats per minute. And so the vagus nerve is constantly stepping on the brake to some extent to keep it at a sort of average level, about 60 beats per minute or so. And then as we breathe, that's changing the baroreflex and the vagus stuff, and the heartbeat speeds up and slows down, and it's sort of the foot comes on and off the brake. But there's this kind of tonic inhibition, where the vagus nerve is constantly at some degree active, unless you have some weird problem and
Right.
you know, you faint and pass out, or you know, the vasovagal syncope, things like that. You see blood and you freak
Yeah.
out, or those kind of things. You get, so the baroreflex, if it's malfunctioning, everybody's experienced, like, you know, if you stand up and you're dizzy for a second,
Yeah.
that's kind of like your baroreflex is sort of struggling to catch up.
Interesting.
Um,
So one of the things you said, and I would just, it's been an interesting thing because I would even say this kind of happened since I've been nerding out about heart rate variability, is the sympathetic nervous system. You know, if you look at heart rate variability, I believe, and I'm going a little bit like into early stages of my own learning curve here, but right when I started to read about this, you'd hear sympathetic activation quite a bit. Sometimes thrown around loosely, but sometimes like there's the sympathetic activation and then there's the parasympathetic or ventral vagal brake. And
yeah,
become more sympathetically active. However, recently I've heard more of no, we're just like the brake is not as strong. So we're not necessarily seeing increased sympathetic activation. We're seeing less ventral vagal braking. However, when you go to
yeah,
the reflex, there seems to be maybe sympathetic activation still going on. So I don't know if we've
yeah.
settled the science on this yet, but I just love to get sort of where you're at. And I'm not going to hold you to this a month or 2 months or two
Uh,
years from now
sure, yeah.
with this, but
I'll
love to get your
I'll give
thinking.
my current understanding. So yeah, both of those are correct. And from an HRV perspective, when you look at the frequency domain metrics, there's very low frequency, and high frequency. And in the beginning, it was back 1996 or so, there was the big paper that got published, like, you know, Malik et al., everybody refers to.
Yes.
And that kind of was the gold standard of, okay, these are the things we're going to measure,
Right.
and, you know, what we think they mean, and how to measure it, you know, as a gold standard.
Yeah.
So back at that time, it was kind of popular to have this notion that there was this, it's called like sympathovagal balance,
Yeah.
which is like, it was thought that it was kind of either one or the other, that it was this kind of, you know, balance of the scales. And so there was a metric that they would measure, like the ratio of high frequency to low frequency, and be like, oh, this is the sympathovagal balance, we're going to use it to test stuff. And turns out that's not really
Yeah.
totally accurate.
I
So
kind of unfortunately, because it made sense.
it's not that simple.
Yeah. I mean,
but
it was kind of
but
like
it's not that much more
nice, but
complicated
yeah, I
either.
know. Like,
So so yeah, but generally, so very low frequency changes in the heart rate are due to like long-term things like diurnal variations, or changes in temperature, or things that your kidneys do, if I recall correctly. And then so that's very low. Then there's the low frequency is basically what they were calling sympathetic. So the baroreflex exists in this low frequency zone, the 0.1 hertz. When you're not breathing in a slow paced breath manner,
yeah.
it's the sympathetic tone. These Meyer waves, they're like slowly flexing, and it's kind of like I don't know, like the salmon in the stream or something.
Yeah.
They're like, you know, swimming upstream. There's these oscillations that happen. They're kind of microscopic, but if you look really close, you can measure them, and that's the 0.1 hertz frequency. That's where you could think of it as sort of the baroreflex is idling a little bit, but there's actually a sympathetic. It's actually a sympathetic origin. Like, they've done some weird blockades where they use drugs, or they'll,
Yeah.
like, you know, cut the spinal cord of a cat and do some freaky stuff. And they can sort of take out parts and see, oh, this is still working, so that must mean it's connected to that.
Yeah.
And so there's still kind of questions of the origin of these Meyer waves. It was named after this guy, Professor Meyer, or some German guy, Mayer, and it's these subtle oscillations in the vascular tone, and that's of sympathetic origin. There's some kind of like pacemaker things for that 0.1 hertz somewhere in the brain.
Yeah.
but then it also gets reinforced by the baroreflex, but its origin may not be the baroreflex. So it's like all these kind of independent cells that are pulsing, but somehow they synchronize together, and it's still a little bit mysterious, but very fascinating area. So the low frequency range was said to be sympathetic back, when they were putting the stuff. And high frequency is the things that change fast, and that would be the vagus nerve, which can activate because it's myelinated. It can have like very fast impulses, whereas the sympathetic nerves, you go more from the it's called the parasympathetic is cholinergic, so it's acetylcholine is a neurotransmitter, and that has the fast effect because of the vagus nerve, I guess. And the other one is adrenal, the adrenergic effect, and so that's what is it, epinephrine or adrenaline? The same thing, or norepinephrine. So that's the sympathetic neurotransmitter, and that's a little bit slower to respond. So it's that's why it's in the low frequency zone, but the high frequency is faster to respond. So the acetylcholine is faster, it gets metabolized and used up quicker. Whereas the other stuff, like if you get an adrenaline rush, it's not a matter of seconds, it's a matter of minutes, right?
Interesting.
So, and then the hormonal stuff is even slower. That's the kidney, very low frequency stuff. So you can think of those time ranges as, the period of time is inverse to a frequency, like from an engineering perspective.
Yeah.
So they're related. So the high frequency, low frequency stuff, the biggest source of heart rate variability in the system, in a human and in all animals, I think, is the respiratory sinus arrhythmia, which is the vagal the vaguely mediated changes due to breathing.
Yeah.
And so that is like by far the most energy in the HRV.
Yeah.
And especially, when you do resonance breathing through HRV biofeedback, what happens then is that I described it in the talk that I gave a while back at Consciousness Hacking. It was sort of like the wind and the chimes. So like the chimes are the baroreflex is this kind of chime that's a sort of dormant thing, like, the Tibetan bowl or whatever. It's kind of just sitting there. It has this resonance, but it's not until you ding it or you rub it that it actually sings. And so it's the breath that is the stimulus that's rubbing the reflex, and that makes it sing and resonate. So there's a graphic that I have somewhere that maybe I could share with you later. You could put it in the slides or something. And it sort of shows that there's this sympathetic aspect of the baroreflex at 0.1 hertz in the low frequency zone. And it's just kind of sitting there slowly doing its thing. And then there's this large energy of the respiratory sinus arrhythmia in the high frequency. But when you slow down your breath, it's no longer in the high frequency zone. It travels down to the low frequency zone, and they come together and they reinforce each other. That's what resonance is.
Okay.
So that's why you can't just say, oh, high frequency HRV is the vaguely associated stuff. That's not true if you're breathing at a slow rate. So that's where people got mixed up, and it doesn't apply when you have paced breathing at low rates. And that also gets into, in the time domain, you have RMSSD, which is people use as a sort of correlate proxy for the vagal associated HRV, which works fine if you're just resting and breathing spontaneously at a faster rate. But during slow breathing, that no longer applies. So RMSSD is not a vaguely associated thing if you're breathing slow. And that's something that I want to sort of write like a sort of critical appraisal paper about, because it's just like the sort of sympathovagal balance has been debunked. I think that this should be debunked too, that it's more complex if you're changing your respiration rate.
Yeah. And I think it's a message that, I know that there's some researchers that use more of a paced breathing heart rate variability app for their research and looking at RMSSD. I'm like, well, if people are doing paced breathing and you're using RMSSD as a measure of the stress response, you've just really messed up your data. Like, because of the pace of the breathing, is going to dramatically impact RMSSD. So you're not getting good baseline. You're not getting a good metric of just at a rest, a resting.
Exactly.
You're just sitting down.
You're comparing apples and oranges.
Yeah, exactly.
Not apples to apples.
We shouldn't use that we just got to be careful of the state that we're eliciting with breathing if we're going to use RMSSD as a metric there.
Yeah, it's just not it's not comparable, so it's apples and oranges. You can compare the RMSSD during resonance breathing, to itself, and you'll see that it increases, and because it's kind of a second order effect where like you're getting some sort of like echo effect of the stuff rather than just measuring it directly. So it's very indirect. And the best way to measure it is just getting RSA. And so there's something that I developed with PranaWave as a way of measuring the RSA like directly in real time. And I realized that Stephen Porges was doing that like 20 years ago or so.
Good company.
It's called like the Porges Borer method or something like that. It's this other guy Borer that he did it with. But so back to the Baroreflex. Do you want to talk about like the components of the Baroreflex?
Yeah,
and
let's do that, because I think I think some of our listeners, like guys like talking about the components of it and any connection again with the systems that we talk a lot about, which you've already discussed in great detail. So let's break it down. Well, what are we talking about with the system itself?
Yeah, so I have like a little picture that I drew that I can, maybe you can put in the slides or whatever.
Sounds good. And I'll let you, if you want to share your screen for our YouTube folks. I don't know if you want to do that.
Yeah, I just drew it on by hand. So
okay, well, we'll throw it in the show notes then.
I can show you a little brief preview. So this is the heart.
Yep.
And so the sinoatrial node is there. So the blood's coming in the vena cava. There's the superior vena cava and inferior. And then you have the aorta, which is where the blood pumps out. And this is called the aortic arch.
Awesome.
So the sinoatrial node is innervated by the vagus nerve, the vagal afferent, that is the brake. So that's one aspect of the Baroreflex. Then there's these stretch receptors, which I didn't draw on there. This was my first diagram. So the green, these little springy things.
Yeah.
So those are stretch receptors, which are called baroreceptors.
Okay.
And so when they stretch out, they kind of fire the neurons, and then so the pressure acts as it's a pressure sensor because it's the little spring gets stretched out by the pressure.
Okay.
So there's a big one in the aortic arch that is innervated by the vagus nerve.
Okay.
I think it's called the pressor nerve or something. It's a branch of the vagus nerve that goes up there. This afferent, and then the other major baroreceptor is in the carotid artery in the neck.
Interesting.
And so it's called the carotid arch.
Okay.
There's also chemoreceptors there that measure like carbon dioxide and pH and stuff.
Huh.
And I don't know if it's the vagus or no, it's actually the glossopharyngeal nerve is what picks up this one. Okay. So glossopharyngeal, glosso means tongue and pharyngeal means throat. So it's like the tongue and throat nerve of the cranial nerve. So those two stretcher things, there's some other minor ones in the heart as well, but like the major ones are in the aortic arch and the carotid sinus. So sinus just means kind of like cave, basically. Yeah. It's a little tiny cave with some stuff in there. And so those two afferents from the vagus and the glossopharyngeal nerve, they go into what's called the solitary tract, the nucleus of the solitary tract, and that's a part of the brainstem. Okay. So it's actually there's something called the vagal nucleus, which is like all the vagally bits in your brainstem, and inside that it has 4 different things. There's the solitary nucleus, the nucleus ambiguus, the dorsal motor nucleus, and the trigeminal nucleus. So the trigeminal one doesn't really have anything to do with the baroreflex. It has to do with like pain in your face and eyes and stuff. So but those are the sort of sensory. So the nuclear the yeah the sorry, nuclear tract of the solitary nuclear tract. It has like a couple different, like some people call it the NTS, or just like sometimes the words are in a different order, maybe because it was in Latin or something. So I got confused for a sec. And so I wrote here on my paper, it's the primary viscerosensory relay station. So viscero meaning organs,
Okay.
and sensory meaning, so it brings the vagal afferents, not just the vagus nerve, but also the facial nerve of the tongue, which tastes, and the glossopharyngeal nerve, which is kind of getting the stretch receptors, and we're also kind of tasting the pH and the carbon dioxide in our blood, or oxygen.
Yeah.
So all those inputs go into the solitary tract, and so it's the afferents from the heart, the lungs, the digestion. That's all visceral.
Yeah.
And the taste. So the taste is additional sensory. So that's why it's called viscerosensory. So all those inputs. So that's where the input from the aortic arch baroreceptor and the carotid arch, carotid sinus baroreceptor, those go into this relay station, the solitary tract in the brainstem. And from there, it sends it up to some other part of the medulla that goes into, decides whether to go sympathetic or parasympathetic.
Okay.
And so that's based on
Stephen Porges, that's that neuroception, if I'm correct, right?
Yeah, I mean this is a little bit more primal, where it's like just the parts that are like mostly like pumping your blood and breathing and stuff. So the emotional stuff where you're looking at safety and things like that happen in higher parts of the brain. It's
but
more
kind of the
a
unconscious part of neuro. That's I always think of neuroception of one, yeah, we can assess and we can do all that, but like in the background, we're always, we're always sort of like if you're driving down the highway, you can be in, doing good heart rate, but then somebody swerves over your lane, that danger is pretty. You don't have to think about, oh, I wonder if this person's going to hit me or not, or
I mean, some people talk like it's the reptile brain or something, that's kind of like keeping you, is the part that's very primal that keeps us alive. So yeah, you're right. I don't know the exact definition of neuroception, but there's other parts of the brain that control heart rate variability that are more in the prefrontal cortex.
Yeah.
And that has to do with heart rate variability and emotional stuff. And so this is a little more primal. It's in the brain stem.
Yeah, but I think that's what Porges means with the neuroception stuff of just background.
It goes through. They're like they go through, like everything goes through the brainstem. The vagus nerve goes. That is where it enters, but then it climbs up into these other parts and does more complicated things. But I'm not getting into that today. To say that for Porges to explain. But so these two parts, so in this these parts of the medulla, it's called the like rostral ventrolateral medulla and the caudal ventrolateral medulla. So rostral means nose, so it's the part in front, and caudal means tail, so it's the part so nose is up and tail is down. So the rostral, so the upper one, so it's this medulla part that does the sort of sympathetic, it's called disinhibition. So like it's kind of like it has this teeter-totter effect of like when it needs to pump up the jam and get your heart beating faster, it's got a but so normally that part is sort of has a lid on it, and then it's not like the vagal brake, because that's purely a parasympathetic thing, but this is a sympathetic, it's its own kind of sympathetic brake sort of thing. I might be getting it backwards, but it's called disinhibition, and so basically it's sort of like release the active part that's gonna, so it's called vasomotor, meaning the motor is gonna like pump your veins to get smaller, tighter, and increase your blood pressure, or it's gonna tell your heart to like pump harder and faster. It's called the stroke volume. So
Okay.
those are the two sympathetic loops of the baroreflex, is the vascular tone, which is how tight your vessels are, and the stroke volume, which is how hard it's going to pump. And then the other one is the sinoatrial node, is sort of like how fast or slow is it going to go. That's different than how hard it's going to pump. So the
Gotcha.
faster slow part is controlled by the vagus nerve in the sinoatrial node. So
So,
all those three
so,
things.
so if I'm like you said, pumping up the volume, so to speak, and getting pumped up for whatever nowadays I get pumped up for, which is a little less in my 50s than it was in my teens and 20s. But like, because I mean, I think one of the things when we took away kind of sympathetic activation, so to speak, and like I remember as an athlete getting really kind of pumped up for the game. It did mean I was in danger, so to speak. I knew I was safe. I wasn't.
Yeah,
I mean, I played basketball, so I wasn't in
it's
like,
called mobilization, so
yes,
it's like, it could be, mobilization can be for play or it can be for defense.
yeah,
So but yeah, so if you think of the heart rate, normally it's got that vagal break, so it's maybe 60 beats per minute, and then
yeah,
you have the RSA that's making it go up and down with your breath. And then you get a little bit excited, the vagal brake can pop off a little bit and give you a little extra
yeah,
go, but then you can relax again really easily. So
yeah,
it gives because the vagal brake aspect is very fast, it can kind of also sort of disinhibit the thing, and you can get a little extra boost without having the expensive metabolic cost of getting an adrenaline rush.
awesome,
So,
yeah,
but then if you're actually exercising, then you do get that adrenaline effect, and the heart's beating faster, and then the blood pressure has to get regulated. If the heart's beating faster, then it has to relax the blood vessels a little bit in order
yeah,
to keep everything in balance. So the baroreflex, its function is homeostasis, which is like to create a sort of equilibrium so that everything is smooth and easy and you don't pass out.
yeah,
So it's constantly working to make everything seem normal and regular. But behind
yeah,
the scenes, it's sort of pulling these levers and pulleys and stepping on the gas and brake, but it's all happening unconsciously. And so the autonomic,
yeah.
means it's automatic.
Yeah. So I would love to get, I know it's a term that's familiar probably with the majority of our listeners, but I'm curious to hear your definition of homeostasis as it relates to this complexity with it. It's a term we do throw around a lot, but I'd love to get David's definition of homeostasis.
Well, I just looked it up in the dictionary the other day. Let's see if I remember. So like homeo means like the same, and stasis means sort of like staying. So it's like basically trying to keep everything the same, sort of even keeled.
Yeah.
But within that, there could be a lot of stuff happening to sort of counterbalance. So it's like, behind the scenes, things are happening, but the end result is things are normal, and
Yeah.
that you don't want stuff to be bouncing around to extremes. You want it to be contained within a certain, thing. But there's another term that's like kind of like dynamiostasis or something. I don't remember what the word is. And
Hmm.
it's kind of a more modern take that like that, healthy function is has this kind of symphonic effect where there's all of these uh co-resonating, harmonized frequencies. So,
Interesting.
you could think of it as like gears spinning or something, and the different gears are interacting, and then you got the conveyor belt moving, but there's all these different sizes and shapes and frequencies that are happening. So, with heart rate variability, what was surprising, when it was first being studied, was like, whoa, actually the variation is good. At first
Yeah.
at first
Yeah.
they were just like, why is it so bouncing all over the place? Like we thought homeostasis was like it should just be flat.
Yeah.
And it turns
Yeah.
out that it's the dynamic energy of resilience or adaptivity is able to respond to the varying conditions and needs of life. And so having that variation is actually health.
Yeah.
And so when it's in a rigid thing, then that's not healthy, as
Yeah.
as we've discovered in the last 20, 30 years.
Well, when I'm just blown away, and now we could save this for either a book we'll write together or another podcast episode. But like the idea of the all this is really happening below consciousness for the most part. So all this complexity that you're describing is really kind of brainstem down, it's obviously integrated into the whole body system. But I just think about like if you look at, sometimes we use homeostasis of, adapting to changes in our environment and matching kind of our internal state to the stress or challenges or demands of the environment around us. So we may need a little bit more energy or relaxation, whatever it might be. And then all this is being fairly managed for us underneath consciousness, neuroception. I think how Porges talks about, am I safe or am I in danger? You're probably not having that conscious thought throughout your day. But if you need to go full sympathetic flight response because you're driving, somebody cuts you off in traffic, that's going to happen immediately for you without kind of a conscious thought. And it's just fascinating to me that this is all happening under consciousness. So, we can think about, how do I get on top of my inbox today? Like it just blows me away that this is happening without much conscious thought, unless we do some like HRV biofeedback, then we're obviously hacking into this system in a way to improve our resilience.
But so it's a friggin' miracle.
It's spectacular.
It is the primal intelligence that beats our heart, is the life force. In Eastern, in yogic philosophy and stuff, they worship these divine principles that are part of creation, and as gods and goddesses. And so there's like, the goddess Kundalini is like the radiant effulgent life force that permeates all consciousness. They have, like Shiva and Shakti also is kind of a dynamic of like consciousness and, dynamic energy. There's all kinds of different ways to look at it. But yeah, I think of, the primal life force that exists within us is freaking amazing miracle that, that does deserve, praise and, and, know.
Well, and to take that to like my training in psychology from a more Western perspective, like I was probably maybe the last class or two that we did pay a lot of attention to kind of Freud and his thinking. Jung's still kind of cool. You got to throw a little Jung in there, but like that collective unconscious or the ids, like all that talk about unconscious. And I feel like we've thrown the baby out with the bathwater with some of this. Is okay, we can't see the id in a functional MRI, and some of this needed to be tossed aside, at least in my opinion. But now we're back, and I think to bring that unconscious back, in a scientific way, which again, not surprisingly, connects to thousands of years of spiritual traditions out there, I just think is a really exciting place to be if we allow ourselves to go back into, like I said, that bathtub, which we totally, I think a lot of us with neurobiology said, oh, we can just throw off all that Freud and Jung out because we got the prefrontal cortex, amygdala, all this stuff that we know. And yet here we go. If you keep studying the body below the brainstem, it gets very unconscious and very cool very quickly. So I'm just fascinated by that.
I think of the vagus nerve as kind of like if our brain was like, a plant, then the vagus nerve is the roots of the plant that are going all down into the organs. So it is all connected. I mean, mind body is like a sort of, a false dichotomy that's convenient. But where can you say one ends and the other begins? Or that's a whole other conversation. But to what you're saying about brain anatomy and stuff. So my understanding is with functional MRI, that's really allowed us to image these things now even in real time. There's like brain network theory, where they could say, okay, here's how all the parts are connected in functional ways, the
Yeah.
functional connectivity. So, we have the default mode network, you have the salience network, you have, so all these different networks are sort of how they're almost like harmonics of the sort of symphony that's happening. And that's a place where I'm super interested. It's kind of getting into, weird hypotheses, but when you see like the patterns of frequency, like if you put the sand on a metal plate and you play a tone, you get all the patterns.
Yeah.
So there's actually the math behind that is called a Laplacian eigenfrequencies. And so they're like harmonics, just like the Fourier transform. You can say, okay, here's like the bass, the mids, the treble are the different, frequencies. And so the Fourier transform is based on sine waves. And so it's just saying that all frequencies are a sum of sine waves. But you can use a different vector basis, not sine waves, but some other weird waves. And so they do that with the brain with this fMRI stuff. And they're showing these harmonic patterns that you can say, oh, here's sort of the bass frequencies, here's the mids, here's the trebles, and they have actual like three-dimensional structures in the brain. Cool. It's really cool. It's like it's kind of like a spherical harmonic, but the brain isn't a perfect sphere, so they do a little bit different math.
Interesting. So I want to make sure with the time we have left, what else do we need to know about the Baroreflex? It sounds like we can separate it out and talk about it kind of separate from heart rate variability, though like with everything with that mind body system we're talking about, it is highly interconnected at the same time. So, anything else that what else do we need to know?
I think we should mention our dear Yevgeny Vashilo, the godfather of HRV biofeedback, who was doing the research on the Baroreflex, and of course there are other researchers found this as well. He wasn't the only one, but he took it really far with the biofeedback aspect. So he developed this model of the different loops of the Baroreflex. So so in sort of engineering network theory, like there's something called feedback control systems, which are part of those sort of robotic things that, if you have, I can't think of it's sort of like a shock absorber kind of thing where, it involves like differential equations and weird stuff. But, if you go over a bump, the shock absorber kind of absorbs the shock. And so that's what the Baroreflex is doing too. It's kind of absorbing the shock of, oh, you stood up, oh, you sat down, you're laying down, you tilted at some weird angle. And so it's sort of absorbing the shock to create the homeostasis so the conveyor belt gives you a smooth ride. But within that, from an engineering perspective, you can look at the math and sort of decompose it into these different loops. So you follow the loop through the vascular tone part, you follow the loop through the stroke volume, you follow the loop through the cardiovagal aspect. And those loops have resonant frequencies, basically. So like, if you think of like, I don't know, like, like an ocarina, like those whistles, they're little, so it's like it's a hollow thing that you blow on and it has a tone, right? But if you have a bigger one, it's a different tone. And if you have a smaller one, it's a different. So the sort of size of the loop has to do with what the frequency is, basically. And so these different loops, so for instance, there's a vascular tone loop, which has a resonant frequency around 0.03. So it's like more than half the frequency of the regular 0.1 hertz loop that we know, which is kind of the cardiovagal loop. So there's these other resonant frequencies, and that's something that I'm very interested in. And there's been the research with the muscle flexing. You can resonate those lower frequencies because it's more difficult to breathe that slow. It's possible. I can do it because I practiced a lot. But when you use your muscle flexion, you can experiment with that. And Vashilo was even doing Vashilo and Lair were research partners in their lab, and Vashilo's wife is also part of that group. they're doing like emotional surprise pictures or something, where like you look at a thing and it's all like bah, and then you're like, oh crap, and they do that, every 55 seconds or whatever to get the vascular tone loop, and they could measure that it was creating some kind of resonance by like, or another one was paced sighing, where you just go like ah, and that has some effect on the vagus nerve and the blood pressure. So if you do that at the right timing, it's similar to breathing at 6 per minute, but it's like breathing at what is it? It's something like, I always forget the number. Instead of a 10-second wave, it's like a 50-second wave or
Okay.
something. So it's much slower. So it's more difficult to breathe like that, but with these other forms of stimulus. So the resonant frequency of the baroreflex loops, it's plural. There's more than one frequency in there. And so yeah, thanks to Evgeny Vashilo for cracking that nut.
Yeah, so the kind of to wrap us up here, because I believe like every sentence you say we could do, and maybe we'll do another episode on, because this is just absolutely fascinating. So when we talk about heart rate variability, we talk about looking at it as a measure. You could measure, call it resiliency. It's a biometric that's connected to, a whole lot of either disease states or health states, mental health, physical health, social, all these different things that we see, and then we use kind of like, we can use, again, on this podcast, we've talked about a ton of things that we know improve heart rate variability, from HRV biofeedback to anti-inflammatory foods. So we're always kind of working in our HRV nerd arena to improve our RMSSD scores, breathing at a normal rate, everybody. I wonder if the Baroreflex, which hasn't got as much attention, at least in popular literature, is there, when you think about it, are you trying to improve anything with that? If we improve resting heart rate variability, are we like doing something good, or does it just like exist? And as long as something's not clogged up, it's just gonna just keep doing its thing in the background.
Yeah, good question. Well, I have two answers to hit on that. One is, most importantly, let's be more specific about what we're talking about. We're talking about vagally mediated HRV.
Yeah.
So RMSSD is a proxy for that at rest, but the most direct measurement of that is RSA.
Mm-hmm.
And so that's what Porges is measuring with his vagal efficiency metric that he's doing right now. And so let's just call it what it is. It's RSA, which is the vagal afferent. Mm-hmm. So it's how much is, because the reason why it's so important, like we touched on before, in the prefrontal cortex, there's all those emotional circuits.
Yes.
And so that's where you get all of the psycho-emotional well-being and even the enhanced cognitive function. So that's what we're optimizing, and that's what most people are measuring. We're not measuring very low frequency HRV to see our kidneys messing with our cardiac system. I mean, that they know that if you measure that and it's low, it's basically means you're gonna die, because your organs are screwed. So they use that as a prognostic indicator for death after cardiac failure and stuff like that. But that's not having to do with the vagus nerve and this vagally mediated. So there's a term I haven't thrown out there yet. It's called the central autonomic network. And this is the kind of the key word that I'm really into these days. And there's different definitions of it, but it's basically all the parts, that they're connecting for these important functions in the autonomic network, but up inside the brain, not down in the heart, in the lungs, and such. It's not in the brain stem, but more in the central nervous system and all the stuff in the brain. So there's like the amygdala, the prefrontal cortex, the anterior cingulate cortex, the nuclear accumbens, blah, 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 all these parts of the brain. And they're all connected in this very intricate way of some of them are activating and some of them are inhibiting, and it's this whole kind of symphony. And it's not just the nerve, but also the blood flow. And so that's why I'm interested in this neurovascular dynamics. But what we're looking at is the vagal afferent is the sort of input to the central autonomic network, but it's attached to the whole thing. So it's really just kind of like the the back end of it, or the front end, or I don't know. It's just one part of it, and that's the part that we can easily measure, and it's the part that we can easily stimulate using the breath. So it's like a really juicy input to this extremely important system that's controlling our our organs, our emotions, our cognition, our health. And so that's where I would say, like, it's not just HRV, like that's just kind of the tip of the iceberg. It's really the vagal afferents of the central autonomic network.
I never thought someone saying those words would be a beautiful way to wrap up a podcast, but I can't think of any. Yeah, absolutely. You win. Let's just put it like that. David, I just appreciate you, man. I feel like we've only talked for probably 2.5 hours in our lifetimes, and yet I feel like, boy, I hope you're continue to be in my orbit and come nerd out with me again on the podcast. This has just been a really good, fascinating deep dive into, like I said, this complementary, connected, but unique system, separate system, but connected in our body. And I think it's an area that we don't talk enough about in the HRV realm. And hey, I appreciate you doing this deep dive with us. So you're going to send me that beautiful drawing that you made, and we'll throw an NFT it or something like that, because that is a beautiful work of art. We'll throw that in the show notes, as well as information about David and his work as well. So David, I want to thank you, my friend. Like I said, every sentence you said was another potential episode. So I hope to have you back soon, but just appreciate you, your energy, and just your deep thinking about this topic.
Yeah, thank you so much, Matt. I'm so excited to share and geek out about this. I've been kind of a lone wolf, so I'm happy to have more. You
found your pack, brother. You found your pack. So as always, you can find show notes, everything else at optimalhrv.com. Thank you all very much, and we'll see you next week.